Hello, everybody, and good evening in the German time. Welcome to our tinyML talk, analysis of ECG data by energy-efficient decision trees on a reconfigurable ASIC. This is a talk from the German subgroup of the tinyML group. And yeah, the talk will be holden by Tobias Peikenkamp from Hahn-Schickard. We want to thank our sponsors from the tinyML group, ARM, Deep Light, Edge Impulse, EMSA, Green Waves, Latent AI, HOTG, Maxim Integrated, Qeexo, Qualcomm, Reality AI, SenseML, SynSend, and Syntian. Are you interested to be a sponsor too? Please contact Olga at tinyml.org for more information. Yes, the tinyML Foundation have a collaboration with Hexter.io. Here we contribute a tinyML Vision Challenge. The submission accepted until the 20th August this year, and the winner of the challenge will be announced on the 1st September this year, and the main prize is a value from have a $6,000 value. Yes, there are a lot of sponsorships available, so are you interested? You can contact sponsorships at tinyml.org. Yes, our next tinyML talk will be on Tuesday, July the 13th. This will be from Siddharth Talur. He's an associate professor in Bombay, and he will talk about edge-compatible machine learning algorithm for vibration condition based on monitoring of machines. Yes, our local committee in Germany is Alexis Weihnachter. He has a master's degree in control engineering and works at Infineon and developed microcontrollers, software for sensors, fusion control. Then we have Carlos Hernandez Quero. He's software project manager at Bosch. Professor Daniel Müller-Kritschneder, he is interim head and chair of real-time computer systems and professor at the Technical University of München. And me, I'm a research in the field of tinyML in a research company, Hahn-Schickard. Yes, so the talker will be Tobias Peikenkamp. He studied computer science at the Karl von Ostrowski University in Oldenburg, with the focus on autonomous systems and machine learning. After he finished his master, he started working at Hahn-Schickard, where he's involved of analysis of sensor data and the applications of decision tree ensemble techniques. So yeah, Tobias, the stage is yours.
Okay, thank you very much, Markus, and hello, everyone. Today I want to talk about the analysis of ECG data and how we designed a very energy efficient system to realize this task. A little bit about myself. I'm working at Hahn-Schickard-Gesellschaft für angewandte Forschung. We are a company with 39 million revenue in 2020. Around 10 million of them stems from contracts with industry and around 7 million institutional funding of Baden-Württemberg. We had in 2020 256 employees, and we are a member of the Innovation Alliance in Baden-Württemberg. Currently, we have 4 different locations where we can be found in Germany. We have the Microassembly Technology Center in Stuttgart. We have the Micro Information Technology System in Villingen-Schwenning, which is where I can be found, which is where I'm working currently. We have the Institute of Microanalysis in Freiburg and the Institute of Microanalysis in Ulm. To be more specific, I'm working in the AI department of Hahn-Schickard. The focus of our group lies specifically on embedded AI, as we are an institute with a lot of microelectronics involved. This certainly is reasonable. And we also focus on AI and privacy, how we can use, for example, medical records or any kind of sensitive data to train AI models while still respecting any kind of privacy concerns at the same time, for example. Some projects that we're currently working on is some industrial robot interaction with the help of AI. We have a project where we look at a self-learning AI radio location system where we want to locate senders in an environment with the help of AI. We look at skin cancer diagnosis where we get hyperspectral images, which are very high dimensional image data, where we want to diagnose skin cancer. We are looking at an AI hardware accelerator where we want to essentially bring AI onto hardware and improve the AI performance essentially. And maybe just as a quick glance regarding the industrial robot interaction, we see a video on the right, and it's a very high fidelity process. We're looking at the cutting of orchids. If you're familiar with this, if we want to duplicate, if we want to clone these orchids, we have to grab them and cut them in a very precise and specific way. And in this project, we want to use AI for one to grab the orchids. And in the second part, we want to determine a cutting angle where we need to cut the orchids, all with the help of AI. Another project that we are involved in is the AI trainer project. So if you're a small or medium-sized enterprise located in Germany, we offer various trainings or events related to AI, which can help with the development of your application. All this is free of charge. The same goes for if you're located in Schwarzwald, so in the area around us, I want to say. We offer working groups, AI consulting, or co-working spaces in the field of AI, for example. And another thing, if you're located in Baden-Württemberg and are interested in AI, we offer some kind of quick checks where you can see how we can apply AI to your project. For example, if you develop a sensor, want to bring it on a chip, maybe even integrate AI into that chip. This kind of quick check, we offer this possibility to validate this approach essentially. And if you have any questions regarding this, you can also message us. Now to the topic of the project. We have the whole project was developed under the Pilot Innovation Initiative called KI-Sprung. This is a contest held by the Federal Ministry of Education and Research in Germany. The general task was to classify ECG data and detect atrial fibrillation episodes in this data. There are three main factors that we want to look at here during this contest. One is the energy efficiency. We want to design a particular energy efficient system. We want to design a system that at the same time satisfies some accuracy requirements. And the general idea is to have some innovation, some innovativeness into the approach one chooses to participate in this context. At the bottom right corner, we can now see what this ECG data might look like. It's a sample of the data that we got, and we can very clearly see the peaks that are occurring rather regularly here, and each of these peaks is then corresponding to a heartbeat of a person essentially. We can also notice maybe some drift in the data itself. We don't have a flat line with some peaks, but the data has some drift inherently. Overall, the task at the end is to look at 500 different data sets. Each of these data sets consists of 2 minutes of ECG data sampled at 512 Hertz. Generally, it's to be said that the data itself is rather clean in the sense there's not much noise or missing data at all, and the data is labeled by experts. So we have a very clear distinction between healthy persons and persons where atrial fibrillation episodes occur. There were different categories where one could participate in this contest, and we made the decision to participate in the 22 nanometer category for ASICs. The end of this contest was in December 2020, and we got the win awarded in March 2021. And as I said in the title already, we used the concept of a decision tree ensemble to realize a rather efficient approach. To be a little bit more specific about the metrics that we need to satisfy, the contest criteria are that we need to satisfy a minimum recall of 90% and a maximum follow of 20%. That means that we are very focused around the correct detection of actually sick patients. We want to correctly identify 90% of those cases. We have a little bit more leeway for healthy persons, where it's allowed to have errors in 20% of the cases. This is what the metrics correspond to. And only if these two criteria are met, the recall and the fallout, only then the energy efficiency of the system gets evaluated. And in the end of the results we could achieve were a recall of 92.7% with a fallout of 14.7%. And we have a maximum of 42 nanojoule per 2-minute ECG dataset. I will go later into this evaluation a little bit more. So the project had the codename internally as generic, where we use the decision tree ensemble, which is an approach from classical machine learning, where we process features and not the raw data itself. And it's a multi-stage procedure in that sense. This, of course, offers potential for optimization. We have a lot of points where we can add additional optimizations. We have a software and hardware implementation feedback where we can fine-tune the system to specific needs, whether we want to increase the accuracy or the energy efficiency of the system. On the bottom right, we see already basically the whole idea. We have the ECG data that is fed into the system. We have our chip where we have a window controller. So we're using some kind of windowing approach to analyze the data. At the start, we have some peak detection, feature extraction, of course, and in the end, our decision tree ensemble classification, and finally our output where we classify atrial fibrillation or sinus rhythm, which is the heartbeat of a healthy person. Using this approach of feature extraction also enables the utilization of problem-specific expertise, meaning we can only extract those features out of the data that we really need for analysis and basically disregard the rest of the data. And one other advantage is that the classification itself is understandable. If one would like to see why a certain classification, for example, atrial fibrillation occurred, one could go back into the ensemble, into the features that were calculated and trace essentially back which feature was corresponding to a certain vote in the system essentially, which is especially in medical fields of huge interest. Then regarding the feature analysis, we tried different approaches before we actually arrived on the pattern we could see the slide earlier. We started with a wavelet transformation, which achieved the required accuracy in the system. So we were able, so this was very nice to see, but it turned out very fast that this approach would be very costly because on one hand, we have a very big feature set consisting out of around 100 features. And to actually reach the specified accuracy, we would need about 300 trees in our ensemble. So this was one idea we very quickly disregarded after seeing this. Another approach was, of course, just calculating features on the raw data itself, essentially skipping the pre-processing step entirely, where we tried the application of features in time and frequency domain. But with this approach, we could not achieve the required accuracy for the contest. So it was some kind of ideally very cheap pre-processing needed to actually get good and energy efficient classification results. And then we looked at the characteristics of the waveform. If we look onto the right side here, we see what the waveform, a heartbeat of a healthy person might look like. We have this smaller peak at the start, which is called the P wave. Then we have this QRS complex, which is the dominant peak, which is most notable in any ECG data, and which is afterwards followed by a T wave, which is another smaller peak. And there are several different possibilities to go from this ideal heartbeat to classify any kind of anomalies, especially regarding atrial fibrillation. For example, if a person has atrial fibrillation, it might occur that the P wave is absent, so we don't find this initial peak. We can look at the width of this QRS complex that we see down here. We could look at flickering episodes between heartbeats, which we see in the sample maybe down here, which almost looks like noise in the data, I want to say. This might be another idea for a feature, but all of these had no promising initial results, either because we could not achieve the required accuracy or because they are very complex to calculate. And then in the end, we defined our features solely based on so-called RR intervals, which is we have R peak for the ECG data, And what the RR interval is just the difference between two consecutive heartbeats in essence. And we can see in the example down here that we have a very irregular heartbeat, which is one of the, I want to say, main phenomenon of atrial fibrillation. And it has shown pretty early on that we can optimize this approach very nicely and also achieve the required accuracy with this approach. Regarding the peak detection, we also ran through several different trials, I want to say, of iteration of different algorithms. In the end, we stuck to the idea of the triangle template matching approach, which is 4 key steps, which is a high-pass filter, which we see here in the upper right corner. So we take the raw ECG data that we see here, we filter it with a high-pass filter. In the next step, we would get a so-called triangle template matching step, which purpose is to really work out these peaks and really pronounce them in a way, essentially. And as a final step, we low-pass filter the whole data set. So we have this rather clean peaks extrapolated, given out of the raw ECG data. And only then we can look at a moving average out of the data, which defines a search window. Essentially, we can see we have these very few peaks where the data is surpassing the moving average. And this is defined as the area where we have to look for our peak in the data. So the approach is somewhat simple to detect the peaks itself. And here's how this looks like in our system. At the top, we have the ECG data with 2 heartbeats in this example. We can see here the software and hardware implementation of our approach. The most important part here is to run the orange line, which is the moving average, which we see here, and the green line, which is the resulting data that we got after low-pass filtering the data. And we can see that this is marked in blue, a search window, which is very well defined in this area where we can search for a peak. Now, one notices a difference between the hardware and the software implementation. So it might be possible that the peaks that we detect are not completely accurate regarding its location. The window we're looking at might not be very precise, especially if you look into the original data. In our use case, this is not too much of interest, because what we're interested in is actually just the difference between 2 peaks and not the peaks itself. So some smaller inaccuracies, I want to say, are fine and allow us to further optimize the hardware side regarding its energy efficiency. And at this point, are there any questions at this point already? I want to stop for a short moment. And is there anything left unclear currently? Else I will just go on.
Yes, so there's one question. So you told us about the features and the feature detection. Is there any further performance improvements possible, or yeah, do you have another idea to make it more accurate?
Yes, as I said, we already did some hardware side performance improvements, which will result maybe in a somewhat less accurate implementation of the algorithm, but allowed us to save energy. One other idea may be, this is all realized in digital domain. I want to say we had trials during the project where we tried to apply an analog filter to detect peaks, and this had also somewhat promising results, but this was not realizable within the scope of the project. But this might be, for example, a further improvement of our setting here.
Okay, thank you. Great. So yeah, in the moment there are no more questions. So if you ever have questions, somebody here in the talk, you can use the Q&A window on the bottom of the Zoom GUI. Yeah, please go on.
Okay. Then I will go into the optimization of the system. We have 2 overarching goals, because on one side, we of course want to reach our specified precision targets, the recall and the fallout constraints, but on the same time, we want to minimize the energy cost of the hardware in the system. This is some kind of like bounded optimization problem. To solve this problem, we defined some sort of cost function for the hardware energy, so that we could minimize this cost function and essentially get a result that is minimized regarding its energy usage. Another key approach to optimize this whole setting is a windowing approach. So if we look into our ECG datasets, we don't look at the whole 2-minute window, for example, but instead we only look at 16 consecutive RR intervals, and then do our whole classification chain of the peak detection, some feature extraction, and the classification to get a result. And what this allows us to do is terminate the system or the algorithm early if we're confident that we detect an atrial fibrillation episode. And later on, I will show slides where we actually measure the impact this had on the energy usage of the system. So to get to the energy cost estimations, we used simulations of an FPGA. We used Pilote for this task. And what this allows us to do is to simulate the feature calculation and the decision tree ensemble, and to get some idea or some estimates for the cost for the features that we used. Now on the right side, I don't want to dive too heavily into this spreadsheet, but essentially what we have here is a list of different features. And after the simulation, what we got is the energy measured in nanojoule per feature, essentially. And just by a quick glance of these features, we can see that we have some very expensive features, which are like almost 20 nanojoule per feature. But on the other spectrum, we maybe even have features which are all the way down to 0.04 nanojoule per feature. So there's a huge discrepancy in the feature set we initially looked at. And of course, there's a lot of optimization to be made, which features we actually choose in the end to classify the ECG data. Then I talked about the optimization function. The goal is, on one side, of course, to minimize this energy cost. But at the same time, we have to consider the accuracy constraints. So what we did in this case is assign a very high cost to those solutions that could not fulfill the recognition or the accuracy requirements. For example, let's say we just used a very simple feature out of here, which might be very easy to calculate, but it's of no value to us if it can't correctly classify the ECG data. So the idea was to assign a very, very high cost to these solutions. And yeah, this is essentially what I said. We assign a high cost to so-called bad solutions which do not satisfy the requirements, the accuracy requirements, but we assign no additional cost at all for good solutions and just take the energy costs as a goal for optimization, essentially. And this is also not too surprising, but this is how this loss or cost function might look like. What we see here is on the x-axis the recall, and on the y-axis the fallout. And what we can see is this, that we have a very high cost in the end for a recall that is very low. On the other side, a high cost for fallout that is very high. And as we go closer and closer to our ideal scenario, the cost obviously goes down. We can even see down here at the end, we have this like notch or gap at the bottom, which is where we don't assign any cost to our cost function. To tackle this optimization, we used a library called HyperOpt. The big advantage in this case is that we could use arbitrary cost functions, because as we've seen earlier, this function that we use might not be differentiable, and therefore might run into some issues for traditional optimization. And this library allows us to find an optimal solution without worrying too much about the cost function itself. So in the end, we just want to minimize the cost function plus the energy cost that occur for a given solution that was selected. And here is one example of our optimization runs of several iterations. We see the blue transparent background is the same plot, the same cost function that I showed earlier. And each point that we see here is one run of our optimization run. And the darker plots are at the start of the iteration or optimization. and the lighter green spots are marking occurrences later on in the optimization process. And what we can see here is that we have a rather big spread, but a lot of the solutions, especially later on, seem to converge towards the area that we are looking for. We, of course, have some very heavy outliers which are not viable solutions at all, but generally the tendency seems to be around this corner here, which is a very good sign. One problem is if you look into this optimization from another perspective, this is still the same optimization run that we see here. Each plot still corresponds to one iteration run. What we notice by looking at this, we have a lot, or I would say most of these iterations got a very, very high cost assigned. This means that all of these iterations that we see all the way up here are not viable to fulfill the accuracy requirements. And we only found a very set of very sparse solutions that actually meet the accuracy requirements of the system. So there were multiple causes for this behavior. One is that we had 70 different parameters in the systems, where each parameter again might be described by a different parameter space. So we have a rather complex parameter space. One other thing to note is that the parameters of the peak detection have a very huge impact on classification accuracy, because if you remember the drawing from earlier, we can see that the peak detection is the step that occurs first. And as soon as we have some errors within this step, let's say we detect too many peaks or we're missing some peaks, this will have an influence of all the steps afterwards, the feature extraction on the classification. So the whole system is very sensible regarding this peak detection, which is also the cause for a lot of these runs having like the maximum cost, where we have like no correct classification for either atrial fibrillation or sinus rhythm at all. So this is a very sensible parameter setting. And then again, we only look at the rather small amount of iterations, at least compared to the parameter space we're actually looking at, and the fact that the system is so sensitive regarding its parameters. So these might be some problems that have occurred here. Nonetheless, we use these solutions that we found as a base for further improvements. One step here was to verify the parameter selection. That means we looked into the features that were selected in the end, but also looked into the decision tree ensembles if we have sensible parameters in the settings. And in the end, we decided to improve the peak detection through manual work and not through optimization algorithm, and verified empirically that the peak detection was working correct on the ECG dataset. What we did to verify this feature selection is to calculate the feature importance that we see plotted down here. And we can see that there's also a huge difference between the features. We have some very, very important features, some very good features. And on the lower end, we have some features which are barely important, if at all, down here at the bottom. What we then did after calculating this feature importance is we tried to normalize the two measurements that we have, the feature importance and the energy cost. So now we have the energy cost and the importance for each feature, and we normalize this to values between 0 and 1. So if we look, for example, at the first feature here, which is the 50 NN, I will go later into that feature, which has a very huge importance of 1, and also a very huge energy efficiency, also of 1. So this is obviously a very, very good feature to use. And we used this data to essentially compare and verify the feature selection that we got in the end. If we look into the same data set, essentially, but as graph, we can see the same behavior here. We have in this dark red the feature importance, and in this light red the energy importance, and features that have and features at the start here, for example, are very excellent in both domains. They are very important and also very energy efficient. More interestingly, or it's getting more interesting down the way here at the other features, where we have some features which are maybe more important but are also not as energy efficient, also other features which are barely important but very energy efficient to calculate. In the end, what we got was a set of 7 features that we selected. These features are based on the RR intervals, as I told earlier, but we also looked at the difference between 2 successive RR intervals, because what we're interested in is the change of the heartbeat, essentially, and this difference of successive RR intervals measures exactly that behavior. So the first feature was the min-max difference, where we just essentially took the maximum interval minus the minimum interval. We calculated the entropy over both of these sets of intervals, the RR intervals itself as the difference between them. And then we have these so-called NN features, where NN describes a normal to normal interval for a healthy person. And this 50 NN means that we have a deviation from this normal to normal interval by more than 50 milliseconds. So what this ends up to is essentially just a very simple counter where we check whether the difference of intervals is bigger than 50 milliseconds in the case of the 50 NN feature, and essentially just count each occurrence in our window for this feature. And the same idea goes for the 25 NN feature with 25 milliseconds and 100 NN with 100 milliseconds. We have one additional feature, which is very similar, which is also just a counter, but instead of using a fixed threshold, what we used here is a certain percentage of the mean of difference of intervals. This allows us to also analyze very fast or very slow heartbeats and not be subject to this difference between the intervals. And now if we look back into the graph that we created at the end and the selection of the features which are marked down here, I want to say the selection seems sensible, seems feasible, especially the 4 features at the start. I want to say are very easy to agree on. These are features which are very good in both domains. We also chose the entropy features, which are important, but not as energy efficient to calculate. And we have one additional feature, which is the min-max difference in our final feature set, which is very energy efficient to calculate, but not as important for the final result. So we validated our feature set that we got in the end and saw that a lot of the features we selected were very sensible and seemed very good. Now regarding to the classification, we used the decision tree ensemble, which is essentially just multiple decision trees used together. And in the end, we used the sum of the leaves of each decision tree to get to our final classification result. Maybe interesting to note here, as we will see later on, is we used the gradient boosting algorithm to train our ensemble, which means essentially we start with just one decision tree and add sequentially new decision trees to our ensemble to minimize the error on some validation set. And if you may be familiar with the gradient descent algorithm of neural networks, this is somewhat similar, but instead of tuning the parameters, in the end, we add a new decision tree ensemble, which purpose is to minimize the error that is occurring. And in the end, what we got was a decision tree that consisted, or a decision tree ensemble that consisted out of 20 different trees with a depth of 3, and where we had 10 bins for each feature. So essentially we divided each feature into 10 different bins and used these values as threshold for the classification. One final note here that we do not the traditional voting approach that we saw earlier, that we just take the sum of the leaves. Our approach is similar, but in essence, we give each tree a binary vote, which is either 0 for a healthy person or 1 for a person where we detect atrial fibrillation. So in the end, we might get a result that looks like this. We have 20 different singular votes, and a lot of these, in this case at least, a lot of the ensembles voted a 1, so atrial fibrillation, and only some ensembles, some trees voted for a sinus rhythm or a healthy person. We then took this vote and multiplied it by some tree weight that we determined. Essentially, here can we see for each of the 20 trees, we have the tree weights that we see. So the first tree has a weight of 10, and in the end, we have a value of 2 for our trees. And only then we take the sum of all votes that we get by adding these values up And if then these votes surpass a certain threshold, only then we make the decision atrial fibrillation or sinus rhythm. We got to these tree weights by taking the average of absolute leaf values for each tree. What this does, or the reasoning behind this, is that large leaf values have a huge impact on the classification result. So if the weight is also huge, probably means that the values, the leaf values of each tree are also very huge. And what I was referring to earlier regarding gradient descent, we also see that at the start we have the trees with a very comparably big weight, and only at the end we will see that the error gets smaller and smaller through gradient descent. Also the weights of the singular trees get smaller and smaller. I just thought this was very interesting to see in this approach. Now regarding the implementation in hardware, generally these trees have a variable structure with rather complex interconnections and a lot of redundant comparisons that occur to actually realize such a maybe simple decision tree that we see here on this side. What we then did was, instead of using the feature's value itself for comparison, we calculated the feature rank, which allows us to get away with fewer comparisons and lower the data width. So what we achieve in the end is a threshold memory that corresponds to the thresholds of the nodes, which is sorted by its values. And then we essentially compare our feature that we have with its threshold memory to, in the end, get an idea about the rank of the feature where it ends up in this settings. And so this is what this might look like in the end. We have here the same approach for each feature. We have the same idea essentially. We have this thresholds which are ordered here and essentially compare for feature to determine the feature rank, and then utilize lookup tables to get to the actual value of the feature used for classification. And this value in the end is then fed into some combiner logic, which then in the end is only resulting in the class decision. One thing to note here, I can't dive too much into the details that we see here, as the patent is currently still pending in the implementation that we see here. So I can't give any more specifics other than this rough explanation. But generally, we used content addressable memory and lookup tables, hence the name KMLUT architecture for this setting. The settings allowed us the pre-calculation of a lot of partial results, also saving energy like this. We were able to compress essentially implementations by up to 400%. We were able to fetch a lot of the results, a lot of the stuff from memory and use it for calculation. The logic itself in the system is rather simple. We have some comparisons and some combiner logic in the end here, but that's already about it regarding logic. And the setting is completely reconfigurable. So we used in this setting, of course, the ECG data features with 7 different features. One might expand on the settings and add several different features, other feature values to the setting, and use the same architecture, the same implementation. And in the end, we have the combiner, which is also utilizing the weight of each tree in the end to get to the final decision, and also allows for early termination criterion and checks whether we sufficiently accurately detected an atrial fibrillation episode in a given window. Here's how a simulation result might look like for our settings. We have, again, our R intervals, and then we can see here the power usage of the system. We can see that the majority is used by the preprocessing, which is understandable because there's a lot of filtering going on, a lot of calculations. We have then the classifier and the feature calculation at its lowest point, which is understandable because we have a very comparably simple feature set in our example. And this behavior stays the same for all windows that we're looking at. We have here the energy values for each window. We can see that there's some variance in between the windows, because not all windows are the same size, because not all heartbeat have the same length. But generally, the principle holds that we see in earlier windows, and the distribution between the energy usage stays around the same for different windows. And here we see a case where we are able to terminate very early on after only 3 windows and end up with a very easy, very low energy usage of only 15 nanojoules in this example. And what we then did, we took our validation set and tested essentially the difference between using this threshold criterion, this termination criterion, and not using it. And this leads us to, we used around 2,800 files for this validation set. If we don't use this termination criterion, so if we every time use the full 2-minute ECG data set, we end up with an average of 7.1 windows per file. If we use this criterion, so we stop early at some points in time, we managed to drag this average down to 6.3 windows per file. In the same vein, also the energy usage goes down per file. We have 42 nanojoule here without termination, and we have 32.5 with termination. And the most important thing is probably that we managed to save this energy in this part, but we didn't really lose much regarding the recall and the fallout of our system. So we can see that the recall and the fallout are going up by a little bit, but it's still in the same ballpark and still satisfies the criteria of the competition. And then we have another energy breakdown that we can see here. You can see in red that the peak detection still takes up the majority of the system, where we have a lot of internal activity, some switching activity, and only a few amounts of leakage, I want to say. If we look into the classification energy usage, we can see that a lot of leakage is occurring. The same goes for the feature calculation, which are dominated by this cost, I want to say. But the distribution between them is still the same. And while the peak detection itself, the energy usage here over time is not too interesting, one can see in the energy usage the end of the intervals, where we have a small peak in energy usage and power usage during the system. So we can actually see when we are done analyzing, detecting peaks in a window, and then can calculate the features. But other than that, we still see this same behavior that we were seeing earlier. We see that for the peak detection, the leakage itself is rather low. And for the feature calculation, for example, we have dominating leakage cost in this case. So in the end, I can say we used an efficient classical machine learning approach, which resulted in an understandable classification for the user. We utilized a lot of hardware and software co-optimization, where the software was hardware cost estimations to improve the software model. And then again, we could use on the hardware the improved and optimized software model. We managed to develop an innovative classifier, which most importantly utilizes the feature rank to actually access or determine the classification results. And we use this, what we call KI-Sprung architecture, to get these results. And in the end, we managed to achieve a very low energy solution. We have a maximum of 42 nanojoule over a 2-minute data set, with typically around 32.5 nanojoule data set in our system. And then that was it from my side. If you have any questions, or also you want to ask other stuff after the presentation, you can reach me at tobias.peikenkamp@hahn-schickard.de. But other than that, also now will be the time for additional questions. So feel free to ask questions if you have any.
Thank you very much, Tobias. Yeah, it was pretty interesting. Now we will start to have a question poll. Please answer them, and in the meantime, you can bring your question to the pool. So here are a lot of questions in the. Here come some questions, Tobias. So the first question is, can you please explain recall and fallout again?
Okay, sure. Let me just go back to the beginning. We had the information. So what we are interested in is we have some sick patients and some healthy persons. And then, of course, we generate a prediction, which is either sick or healthy. And then we have 4 cases that can occur. One part is how correctly, or the recall describes how good we are regarding the recognition of sick patients. So we're looking into only this part, essentially, of this table that we see here. And we want to know what's the percentage of correct classifications, of correct sick classifications of the patients that occurred here. And this had to be minimum 90%. The similar idea is the fallout. Here we look at it's essentially what's the word for the distribution of the behavior between the false positives and the overall healthy persons that occurred. So we want to follow 20% means that only 20% of the cases where the person is healthy, we are allowed to make an error. And if the person is sick, we only are allowed to make a mistake in 10% of the cases, or the other way around, we have to be correct in 90% of these cases.
Okay, thank you very much. So the next question is, one slide seemed to say you classify as AF or sinus. What about other cardiac electrical problems? Did you test with other issues?
First of all, the approach we got and the data we got were only these 2 cases, so sinus rhythm and atrial fibrillation. So this means that we could not really detect these issues. What we did, there are some public available data sets, and tried to run our algorithm over these data sets. But since we're only looking into the peaks, essentially, or the differences, and there are a lot of other, I want to say, cardiac issues that can occur that also have some variances in between the heartbeats. And in this case, we would always falsely classify this as atrial fibrillation. So our setting is not, I want to say, only focused on the detection of atrial fibrillation.
Okay, thank you very much. The next question, is the data set public? Do you use for the
so the data set we used is not public. It's private, and we signed an NDA for this. There's the MAT database. It's the MAT public arrhythmia database. I think I can find the link if I'm searching for it. But the data we itself used is sadly not public.
Okay, thank you. And then a little longer question. I try to compromise it. So are the RR interval-based features implemented in integer or floating point or fixed point arithmetic in hardware? And did you have used any quantization for the raw ACG data? Yeah.
So we used integers only, I think 16-bit integers. As I'm responsible for the software development of this project, I'm not too sure about this. But yeah, we use 16-bit integers for it. And sorry, the other question, can you repeat it again?
Yeah, do you quantize the raw ACG data in 16 or 8-bit? And yes, this was the other part. But
okay, I just see it. 16-bit, and regarding the other hardware specifications, sorry, but I can't inform you about that, so I don't exactly know the overhead that is occurring.
Thank you. Then the next question, just to make sure I understand, you start in software, you optimize the decision trees, we are going boosting, and only once this is set, you went onto hardware implementation. Is this correct?
Correct, yes. So there's no training on the hardware. If this is what you're referring to, we trained the models initially in software, and once we got to our final decision tree ensemble, we translated this ensemble as is as a whole into hardware.
Good. Then the next question, I would say, we will answer the 3 questions. So do you have a paper about this work?
No, there are currently no published papers for this work. As I said earlier, we have a patent pending currently that is still in progress, I want to say, but that's it currently.
Okay, but will there be a paper about this?
I could imagine, but I'm not sure actually at the moment, so I can't really say right now.
Okay, good. Thank you very much. Then the second last question, you used an FPGA in this project too. Which FPGA do you use?
I'd have to, if I didn't note it here, I sadly can't answer it. I want to say, because we used this for optimization, the actual energy value that we got out in the end was not too important. It's just that we used the values, and the relationship of the energy values is important to us. But I can't inform you about the FPGA we used.
Okay, thank you. Yeah, so how much energy was used to get the data from the ECG sensor?
I'm not entirely sure, because in the scope of this project, we don't actually realize the setting onto a real ASIC and just in simulation. And for this, I can't tell you the values, sorry.
Okay, so one last question. Does the spectrum, so the fast Fourier transformation of the dataset, give any useful information, and how energy efficient would be the FFT?
So first of all, the Fourier transform had some success, but we didn't, not on the raw data. So we initially tried with Fourier transformation on the raw data, but there needs to be some kind of preprocessing to actually get this going. The Rayfield transformation I talked about initially has like the same idea about some frequency domain issues. And this approach, for example, works very, very well. And we had good results with it. I think if we wanted to, we could even surpass our accuracy that we got in the end. But I don't think I have the values here currently, but it was regarding the energy efficiency, but it is way out of scope of our current approach, I want to say. So we were significantly lower than that. I can't give you any more specifics then. I don't have the values here currently. Okay,
thank you very much. So yeah, this was all the questions. So after that, I will end the presentation, or the official part of the talk. Really thank you to the sponsors of the tinyML group. We have the sponsor ARM, the Software and Hardware Foundation for tinyML. Then Deep Light, they used to use AI to make other AI faster, smaller, and more power efficient. And then Edge Impulse, this is tinyML for all developers. EMISA, the I in IoT, and they make Edge AI visual sensors. Then GreenWaves, they're enabling the next generation of sensor and material products to process rich data with energy efficient, latent AI, adaptive AI for intelligent edge. We want to thank HOTG, and then Maxim Integrated, and they're enabling edge intelligence. Qeexo AutoML, this is an automated machine learning platform that builds tinyML solution for the edge using sensor data. Thank you to Qualcomm and advancing AI research to make efficient AI ubiquitous, and to Reality AI to add advanced sensing to our products with Edge AI and tinyML. SenseML builds smart IoT sensors devices from data, and SenseSense to build sensing and inference hardware for ultra low power embedded mobile and edge devices. Yes, to the last sponsor, thank you, Syntax. He's moving artificial intelligence and machine learning from the cloud to the edge. Yes, our next talk will be on Tuesday, July the 13th, next week, about Shitat Talur. It's associate professor in Bombay, and the webcast starts at 8 o'clock at Pacific time. Yes, this was our presentation and the talk, and with the official part. Now the unofficial part begins. Now we will get everybody who's in the talk and to the talk, and then we can chat to each other and connect a little bit. Thank you very much.